right? So if the determinant is non-zero, then you could divide both sides by that determinant, and then you see what the inverse function, what the inverse matrix is, right? You notice that the adjoint divided by the determinant is exactly the inverse matrix, right? And so the inverse matrix is not some sort of arbitrary, collection of numbers. It's in fact exactly, the transpose of the adjoints, transpose of the cofactors, divided by everybody divided by the determinant. Okay, and let me make one remark. The book sometimes one denotes there's actually some conflation of terms. One sometimes calls the conjugate transpose of a matrix the adjoint A star. Okay, that is, you transpose the guy, and then you take the complex conjugate of everything. So it's like a complex, if you've got complex values in your matrix, you take complex conjugates of everybody, and then you transpose the guy. And that's also called the adjoint. Okay. So, but that adjoint is not the same thing as this adjoint. Okay, unfortunately, the term is used to refer to both of these guys. We'll try to distinguish between them by calling that guy A star and this guy adj A. Okay. I think in the book they call this A star the adjoint matrix. Okay, everyone close your eyes for a second. Is there any part that somebody would like to see? If you'd like to see something, raise a finger.
Can you explain a little bit more the last theorem?
The last theorem?
Yeah, I don't recall I've ever seen that.
This thing?
Yeah.
It's not
just that.
Yeah.
Okay.
Maybe have you seen the term permission? Permission? Okay, so you can have well, you've seen the term symmetric, right? You've seen symmetric matrix, and maybe one thing that one thing you might have seen in a linear algebra course is that if you have a symmetric matrix, then you're guaranteed a basis of eigenvectors, and so you can diagonalize. Okay. The same thing is true for complex matrices, which are self-adjoint, so-called Hermitian matrices. So if you have a matrix, right, if you have a matrix that is symmetric, then it has certain properties.
Okay.
For complex matrices, if you have a matrix where the guy is equal to its conjugate transpose, then those things happen. Okay, it's not true for the complex symmetric matrix. What you need is something a little bit more. You need the matrix not to be equal to its transpose, but to its conjugate transpose. Okay, and so these guys are called symmetric. These guys are called Hermitian. So it's just an extension of the notion of transpose for complex matrices. And that's how we use it. Because we're going to want to diagonalize the matrices. Okay. So some stuff that you might not have seen, matrix functions. So you can define a function, say, called A, going from R into the n by n matrices. Okay. So for every time, right? So A of t is a matrix, right? So as t changes, then your matrix changes. Okay, so this is a matrix value function. Call it matrix value function. Right? Takes in a number and spits out the matrix. Right? Okay. Like you could notation for these guys is is the obvious notation. We say we use excuse me, alpha ijt, right? So this is the ij entries function. Right? This is the function for the ij entry of the matrix A. So matrix line function, we can, as you probably suspect, one can define the derivative, right, a prime of t as the limit, right? You define the limit using the standard limit definition, the limit definition. Right? And that boils down to just what happens is that a prime t is just going to be the entry-wise derivative. So you just take every entry and differentiate every entry. Okay. And so like if your matrix function was something like cosine t, sine t, I don't know, maybe sine t, cosine t, right? Then in time you can just differentiating every entry. And similarly for taking integrals, right? If you're taking an integral of this guy, you're just going to take the integrals entry-wise. So the definite integral would be just a constant matrix, right? A matrix of numbers. Okay. Properties of the derivative. Properties of the derivative are what you would expect them to be. Right. If C of t is a constant matrix function, right? It's a function that spits out just the same matrix all the time, right? Then the derivative of this product is just going to be c times the derivative of the function. Right? If a and b are matrix value functions, then you have the product rule, the derivative of the product. Well, that's going to be a times the derivative of the second plus the derivative of the first times the second. That's product rule. I know that in high school, people often say like the first times the derivative of the second plus the derivative of the second times the first, just thing like that. But that's wrong. You see that doesn't work here. You can't say, like people usually say like f times g plus g times f, right? But in this case it's wrong, right? Because that's the wrong order. You need f prime g plus f g prime. And you really need that because matrix multiplication is not commutative. Right? So don't say this. It has to be in the right order. So watch out. Not commutative. Okay. Other things that you should be able to do, solve linear systems using Gauss-Jordan reduction. Like if somebody says, find find, say, a basis of the null space. Of some matrix, right? Somebody gives you a matrix and says find the null space, and just give a basis of that. Should be able to do that. Concepts that we've seen in this class already: linear independence and linear dependence of a set of vectors. And you should be aware of the relation with matrices of the above, the notion of linear independence. So that is, if given a set of vectors vi, given a set of vectors vi, if we create, actually let me look this over here. If we create a matrix A with column vectors vi, so given some vectors vi, if we create a matrix A with these column vectors vi, linear dependence means that there exists some non-trivial vector C such that AC is 0. Right? Because if you have your matrix V1 through Vk, say, and you have some vector C1 through Ck, and you multiply these together, that's the same thing as C1 times the first column, V1, plus C2 times the second column, plus Ck times the last column. Okay, this is the point here. This is the point that matrix multiplication of a vector basically is the same thing as linear combinations of the columns. Matrix multiplication of a vector is the same thing as taking those entries and taking the linear combination of the columns. Okay, so linear dependence would mean that there's some way of getting the zero vector. There's some non-trivial way of getting the zero vector. In other words, there's some non-trivial vector that gives you zero that is in the null space. So this linear dependence means that the null space is non-trivial. Okay. Right, and along the same lines, right, linear independence means there is no non-trivial C such that AC equals 0. Right? There's no way to get the zero vector except by taking C as the zero vector to begin with. Okay, so connecting backwards to what we said about the determinant, right? If A is a square matrix, then the vectors, the columns, are independent. If only if the null space of A is trivial, right? If the only way of getting the zero vector is to hit the zero, is to multiply by the zero vector, right? But we saw earlier that that's the same thing as saying the determinant of A must be non-zero, right? That the matrices will be invertible, right? That A is an invertible matrix. Right, so relating independence back to the determinant. I'm sorry, I'm taking that up. We'll continue this next time.